A mission to rescue a falling space telescope. More uses for the solar gravitational lens. The Euclid Space Telescope images the center of the Milky Way, and in Space Bites Plus, a star ate a planet. All this and more in this week's Space Bites. NASA's Swift satellite has been operating for decades, over 22 years, but it's in low Earth orbit. And so the problem with being in low Earth orbit is that over time, your altitude is slowly going to lower as you encounter more and more air resistance, friction from the Earth's atmosphere. We're at a time when the sun has increased solar activity, as part of its 11-year cycle. When there is more activity from the sun, the Earth's atmosphere responds. And so this is actually degrading satellites faster than normal. And so what's happening to Swift is actually happening to a lot of satellites. And Swift is actually one of my favorite missions. It's this great X-ray observatory that's designed to image a lot of fast-moving objects that are happening in the night sky. Think about gamma ray bursts and things that happen. You want to be able to do a follow-on observation of it as quickly as possible. And like the way Swift works is that it has this one instrument called the Burst Alert Telescope. And this is constantly scanning about a sixth of the sky for any interesting event that goes off. Then when it detects something, it quickly turns and begins imaging the afterglow of that area in X-rays and in ultraviolet. And this gives you the first moments after a supernova or gamma ray burst goes off. And often this is when the most interesting part of this event is happening. So Swift was designed to put eyes on more gamma ray bursts and supernovae than any other telescope. It wouldn't luck out. It could spot them out of the corner of its eye and turn and watch it. And Swift is still working great. The problem is that its orbit is decaying. And so when it was first launched 22 years ago, it was at an altitude of 580 kilometers. And now, after decades in orbit, the air resistance from just being in the Earth's atmosphere has lowered that orbit down to just around 360 kilometers altitude. And the problem is that that is now going to accelerate. The lower you get into the atmosphere, the more air resistance you experience, the faster your altitude drops. And it's just a matter of time before this spacecraft would burn up in the Earth's atmosphere. But because it is working perfectly, NASA wanted to see if they could rescue it. So they contracted with a company called Catalyst Space, and they built in just 9 months a rescue spacecraft called Link. And I think one of the kickers for NASA is that the budget for this mission is extremely cheap. It's about $30 million. And when you consider that the budget for the development and launch and ongoing operations of Swift is in the hundreds of millions of dollars, this is a bargain. The plan is that Link is going to launch on a kind of older launch platform that we haven't seen very much. It's called a Pegasus rocket. This is carried under the wing of a Lockheed Martin carrier aircraft to altitude. The Pegasus drops off the wing and then carries its payload up into orbit. Once it's in orbit, it will maneuver and rendezvous with the Swift satellite, grab on, which Swift was never meant to do this, and then try to push it to a higher altitude. And if this works, then they should get at least another 10 years of operations out of the Swift mission. And the Link mission is due for launch on Saturday. And so now we're going to know if it's possible to raise the altitude of satellites that are working well. They just need more time in orbit. So we've done a ton of reporting on the solar gravitational lens. I almost think that we are the solar gravitational lens channel. If you want news on solar gravitational lens, this is your place. I have interviewed Dr. Slava Turyshev, who is the mind behind the solar gravitational lens, multiple times, and we report on it on Universe Today. It feels like almost on a weekly basis, just because there are so many cool ideas. It's probably not that much, but it is a lot. And so just this week, Dr. Slava Turyshev released a new paper where he proposes some other uses for the solar gravitational lens. And so if you aren't familiar, this is where you take a spacecraft out to a point where the sun acts like a natural telescope lens. Its gravity distorts light, focusing it so that you can see stuff on the other side with higher resolution. And the dream is that you could put a spacecraft at this point and then you could observe Earth-sized worlds orbiting around sun-like stars within the habitable zone at a crazy level of resolution, like 1,000 by 1,000 pixels. You could see the planet. But there are a lot of challenges to using the solar gravitational lens for that purpose. Astronomers are still kind of arguing about whether or not you actually would get that kind of resolution. Would you be able to see features on the surface? What damage to your observations does just the cloud cover on that planet do? So this is all still up in the air, but that is, of course, the dream. But Dr. Turchev says, well, there are other things you could use the solar gravitational lens for. In his paper, he provides just 3 examples, but I'm sure this is just the beginning of what is possible. So one idea is that you could map the surface of a white dwarf star. And so white dwarf stars are dead stars like our sun. And really, they are the revealed core where all the fusion was happening. But now it's died, sloughed off its outer layers, and you've just got this rapidly spinning ball made of carbon or heavier elements as well. Are they just like a perfect crystal, a giant diamond? Or are there surface features, mountains, and other stuff that you could actually resolve on the surface? Solar gravitational lens could tell you. The next idea is the work that's being done with the Event Horizon Telescope here on Earth. This has allowed us to reveal features around the event horizon of the supermassive black holes at the heart of the Milky Way and at M87. And this is kind of the limit. You know, this telescope, the size of planet Earth, has been able to just reveal the shadow of the event horizon around these black holes. Dr. Turchev says, well, you could boost that to several orders of magnitude. And so you could get in much, much closer, maybe get into the photon ring and eventually see right to the very edge, to the event horizon of this black hole. But of course, if you're going orders of magnitude, then you could also look at other black holes. And so not just these 2 that happen to be the largest in the sky, maybe you could get hundreds, maybe even thousands of other black hole event horizons. And then the third idea, it's the one that I think I like the best, is that you could directly observe protoplanetary disks. And, you know, we've got great examples of protoplanetary disks seen from ALMA and other instruments, but you're just seeing this flattened protoplanetary disk in space. And a hint, like you can see where there might be planets forming gaps in the disk and so on. But with this kind of resolution, you could zoom in on very specific parts of the disk and actually watch these planets forming around this young star. And so this is, again, just sort of a brainstorming of ideas for what you could use the solar gravitational lens for. And now it's just a matter of getting out there. And that, of course, is the challenge, that you're going to this place that is more than 500 astronomical units away from the sun, much farther than the Voyager spacecraft have gone in 50 years of travel. So we would need some kind of faster propulsion system to get us out to that point to make these observations. But if we could, then the science that we could do would be incredible. And we've got a story about this from Andy Thomaswick. There are some great astrophotos of galaxies that are mid-collision or recently collided or are just the result of a collision, that the galaxy looks strange and it couldn't get that way unless it had recently gone through a collision. These are like one-offs, but in the early universe, galaxies were much, much closer together. Astronomers were looking at what they thought was a very large, massive galaxy early on in the universe. They were seeing it at a time when the universe was around 1.5 billion years old. But when they did observations in various wavelengths with high resolution, they realized this isn't one large galaxy, this is 6 galaxies in a galactic pileup, all smashing into each other at the same time. And the astronomers proposed that, in fact, what we're seeing is a proto-cluster. You know, we know of clusters that can contain hundreds, even thousands of galaxies today, and they're all sort of buzzing around each other, that they have this giant dark matter halo that stretches between them. But how do you go from the cosmic microwave background radiation to these giant galaxy clusters? Well, you had to have intermediate steps as well. And so this looks like an example of a protocluster, just 6 galaxies coming together, beginning the party that may then have later gone on to have many more galaxies in it. And it's important to note, right? These aren't dwarf galaxies coming together like building blocks to build one galaxy. These are proper large galaxies, and that this combined object is going to already be a very massive galaxy. When the astronomers looked at how these galaxies were coming together, it was very satisfying because we have these simulations of the early universe, and now the actual observations, the actual galaxies coming together match the simulations very well. And like, that's really the point of simulations, is to help you predict what you should be able to see out there in the universe. Got a story about this from Evan Goff. Most of the large stars in the universe are part of multiple star systems, binary stars, triple star systems, even up to 8 stars in a single system. But If the stars get close enough, then they can start to feed off of one another. Whichever is the more massive object can actually start pulling material away from the other. And if they get really close, they can actually exist in a common envelope. So astronomers have found a situation where there is a white dwarf star that is orbiting around a main sequence star. This is common, and this is the kinds of events that will give us novae. So you get material streaming off of a companion star. It builds up on the surface of the white dwarf. It reaches a certain temperature on the white dwarf, and then it flashes off in this thermonuclear explosion. And another flavor of this gives you the type 1a supernova that can detonate and just sort of destroy the white dwarf entirely. And there is this theoretical limit about how close these objects can get. They shouldn't be able to orbit each other less than about 76 minutes. And this is this sort of theoretical limit based on the size of the star and how the gravity works. But the universe doesn't follow these rules, and astronomers know of 9 examples where the two stars are orbiting around each other faster than that 76 minutes. Now astronomers have found the 10th example of this. This one is fast. It only takes 72 minutes to complete an orbit. So how could this be possible? Well, astronomers think this is telling us something about the companion star, that it might actually be a lot more dense, or maybe it has heavier elements, or it's largely helium and sort of nearing the end of its own life. By finding examples where you've got stars that are orbiting around each other too quickly, this might give us some example about how these binary systems reach their end. Got a story about this from Mark Thompson. Every week we do a vote on our channel where you tell us what you thought was the most important space story of the week. And the winner last week was exoplanets found with soot. Thank you everyone who took the time to vote in our poll. Now we're going to put this week's poll into the post tab here on our channel. It's there right now, so you can go and vote, or just subscribe to the channel, click on the notifications bell, then go to the post tab, vote a bunch of times, and then you should see that vote every week. All right, we got another story about the early universe. In this case, it's about a galaxy that is seen in about the first 700 million years of the age of the universe. And this is a time called the epoch of reionization. And this is a time when the universe was dark, but the combined radiation of all of the galaxies and the stars in the universe were starting to heat it up and make it transparent again, turn things into neutral hydrogen. Galaxies seen at this time are very, very important because it's just incredibly important transition time in the age of the universe. So we've got new observations from a pair of radio telescope arrays. One is the Very Large Array, the big radio telescopes in the US. The other is the Atacama Large Millimeter Array, or ALMA. And James Webb has found several examples of galaxies like this, and found that they are unusually large and bright. And I think you probably remember when James Webb first came out, we had this controversy about how it was finding these large, bright galaxies. Maybe they were starting to challenge the existing theories of how the universe evolved. That concern has gone away, but still there are very interesting galaxies out there. And so one of the big questions is how these large galaxies got so much material early on. How did they grow so quickly? With the VLA and ALMA, they're able to observe the area around this early galaxy and see how it's funneling gas into the central region to help build up this galaxy early on. And so normally they have to kind of just infer how much material came into this galaxy. But with these observations, they can actually see it falling in at a time when the universe was only 700 million years old. Got a story about this from Matt Williams. You've probably heard this quote that most stars are in multiple star systems. And that's not entirely accurate, because the most common star in the universe is red dwarf stars, and red dwarf stars are mostly singletons. But when you get larger stars like the sun and bigger, those are more commonly in multiple star systems, binary star systems or more. And when you have massive stars, they can go supernova. You can get a neutron star as a result, or you can get even a black hole as a result from these stars going supernova. And you can have many situations where you have two massive stars that are orbiting around each other. One goes supernova, and then the other goes supernova. And now astronomers think they've found an example of this. And it's actually a fairly famous supernova remnant that we've known about for a long time, called the Jellyfish Nebula, also known as IC443. It's about 5,000 light years away, and we know that it was caused by a supernova that went off about 8,000 to 9,000 years ago. And astronomers are able to detect gamma radiation and X-ray radiation that is coming from the region around the supernova, where hot gas is slamming into the interstellar material and giving off this additional radiation. But astronomers also knew of a second source of radiation in the area, another place where material is piling up against the interstellar medium and giving off X-ray radiation. And now they've worked out that, in fact, it was a second supernova that went off at roughly the same time, astronomically speaking. What astronomers think happened was tens of thousands of years ago, there were two massive stars in orbit around each other. One of them detonated, and that caused the other star to be flung away. And it had then been moving through space for tens of thousands of years. And then it went off as well. And so we've got this overlapping double supernova. One could be up to 100,000 years ago, while the other one happened more like 8,000 or 9,000 years ago. And the two centers of the supernova are separated by about 40 light years. Got a story about this from Evan Goff. Don't forget to like this video. It only takes you 1 second, and yet that helps this channel. And as you know, I like to share cool pictures with you, and this one is an absolute stunner. The picture of the year? Maybe? I'm not sure. This was taken by the European Space Agency's Euclid mission. And we've done a lot of reporting about Euclid, how it is going through this process of mapping out the sky in visible light and infrared and helping astronomers figure out the locations of dark matter and try to understand the influence of dark energy over the age of the cosmos. But it is just an incredible visible light observatory. And astronomers recently pointed it at one of the most action-packed places in the night sky from our perspective, and that is the center of the Milky Way. And so look at this picture, and I'm sure we're only going to be able to show you zoomed out versions or tiny little slices or drifting scans of it, but there are 60 million stars in this giant mosaic that was taken by the Euclid mission. And Euclid took 26 hours to build up this mosaic. And really, it's one of the most detailed images of the center of the Milky Way that's ever been taken. Each time Euclid points at a spot in the sky, it is 270 times larger than the Hubble Space Telescope. And so why did they take this picture? I mean, it's a great picture and it's just cool to have, but the scientists have a scientific purpose for this, and I think it's very cool. So what they're doing is preparing a before shot of the center of the Milky Way that can then be used to compare when the Nancy Grace Roman telescope launches and begins its science operations later this year. One of the tasks of the Nancy Grace Roman telescope, in addition to something that's very similar to Euclid, is it's going to be looking for microlensing events. This is where you get a star passing in front of another star and it distorts the light coming from that star. And if there are any planets in orbit around the foreground object, then you get sort of an additional blip in the distortion. So now you've got the before shot from Euclid where they see the whole center of the Milky Way, and then you're going to get the after shot or the during shot from Nancy Grace Roman. And then you're going to get follow-on observations from the Nancy Grace Roman telescope, where they're going to look for any differences between the image taken by Euclid and then what Nancy Grace Roman is taking to try and spot the microlensing events. And that'll tell astronomers how many planets there are out there on average. But again, just an absolutely incredible image. I hope you're enjoying this week's episode of Space Bites, but if you're watching this on YouTube, you had to watch an ad at the beginning. Now, there are no ads in the middle, and we don't do any sponsorship ads, so that's the best we can do here on YouTube. But if you're a teacher or you just want to enjoy our videos without having to watch any ads at all, we're hosting all of our videos over on Patreon. And that's completely free. You don't have to become a patron. You can just go over there and watch the episode totally free. But to get you into the habit of watching our videos with no ads, we are sweetening the deal. We've put one additional story in the version over on Patreon. And the additional story this week is about how astronomers have found evidence of a star eating a planet. So I'm going to put a link down in the show notes. You can check that out. And of course, this is just a fraction of all of the stories that we're covering on Universe Today, which is the space and astronomy news website that I publish. Universe Today. That's me. And there can be 30 to 40 to 50 stories every week on Universe Today from a collection of writers. But if you don't have time to check the website every day, if you're not signed up to the RSS feed, then you should sign up to my weekly email newsletter, which I send out every Friday. And it's a collection of all of the stories that we're covering on Universe Today. But I write it myself. There's no ads. It's completely free. Go to university.com/newsletter to sign up. Have you ever noticed that a lot of names in astronomy are really bad? What's that about? We'll talk about it in a second. But first, I'd like to thank our patrons. A special thanks to Abe Kingston, Andrea Bedretti, Brian Bodu, Caradon, Chuck Hawkins, Commander Baylock, Dark Finga, David Gilton, and David Matz, Enthraller Reading and Math for Toddlers, Evan.Pro, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Marcel Smith, Michael Purcell, NASA Ocean Guy, Nordspace, OneStepForAnimals.org. Please follow my nephew at VBrick6994, Rankaidu, Richard Williams, Sean Sargent, Stephen Fallon Mummy, Team 49, Telescopes Canada, Vlad Chiplin, Wolfgang Klutz, and Zelda Fraser will say anything for $100, who support us at the Master of the Universe level, and all our patrons. All your support means universe to us. I got this comment from Jen Dominica. Why are they called data brokers like on a stock market? Do they buy images from the telescope for cheap and then sell them higher? Actually, when I hear the term data brokers, I don't think something about the stock market. I think about the companies that are buying and selling our personal information, and that they are tracking us across the internet. And then there are all these services that will get your information off of these data brokers. So I think when most people hear the term data broker, it's worse than just, some stock market person. It's like data brokers are not loved by people who use the internet, and people will go to great lengths to try and remove themselves off the data broker directories. But when we use data brokers in the astronomy sense, it's perfectly harmless. Very good, in fact. When you have telescopes that are putting out a lot of information, like Vera Rubin and other all-sky surveys that have come before that, it's an enormous amount of data, terabytes, petabytes, and that this needs to be distributed out to the astronomers that need it. The telescope operators, all they're trying to do is make the fire hose go. They're trying to make sure the data is coming off the telescope, it's making its way onto the hard drives, and then it's going to make its way out into the astronomy community. But there's a lot of tools that astronomers need to be able to slice and dice those data. And so they will have data brokers who are contracted by the telescope company to be able to store that information and then provide tools to be able to search through it and package it up in different ways. And so you have some data brokers that are providing information that's useful for cosmology or deep sky or Milky Way astronomy or stuff that's just in the solar system. And so if you're going to try and do some science on solar system objects, you go to the data broker that is containing the information and then access it from there. And you don't have to pay, and they don't also keep personal information about you, but it's a way for astronomers to get information that is prepared for them in a way that meets their needs. That's what the data brokers mean in the astronomical sense. But I think just in general, astronomers do a terrible job of naming things. You've got examples like the Big Bang or black holes, dark matter, dark energy. Those aren't great names. But then you have backronyms where people are coming up with a really elaborate bunch of words strung together just to be able to create a backronym or, an acronym that's just a little too cute. So that's not doing any services either. So I think, someone needs to come along and do a proper job of renaming everything in astronomy. Just, start with the Big Bang, black holes, get to data brokers, dark matter. We'll rename them all and do a much better job of explaining everything to the public. All right. We'll see you next time.